All right, we're in section 11.1. 11.1 is sequences in series. Sequences in series, okay? Well, the sequence, they give us a definition on, we're on page 1006 of your book. Again, make sure you are reading these sections before you attempt homework. They say an infinite sequence is a function. An infinite sequence is a function. Okay? They say whose domain is a set of positive integers. Whose domain is the set of positive integers. Okay? A finite sequence, so this is the definition of a infinite sequence. A finite sequence, so now we're defining that. They say it's a function whose domain is a set, is a function whose domain is the set of the first n positive integers. Okay? So, the only difference between an infinite sequence and a finite sequence is an infinite sequence has infinite number of terms, finite sequence has a finite number of terms. The way we're going to write sequences is we're going to use this notation AN. Okay? AN denotes the nth term of the sequence. AN will denote the nth term of the sequence. So we'll write the entire sequence as a set of all AN. So what this means is, this means that term A1, then A2, then A3, keeps going forever. Okay? That's how we're going to indicate it. And you could write the nth term if you want, and then dot, dot, dot. Okay, that would be an infinite sequence. Because there's going to be an infinite number of terms. Okay? So that's all the sequence is. It's just a list of terms, and it can be finite or infinite. So example one, they say, write the first four terms of the sequence defined by the nth term. So write the first four terms of the sequence. Okay? So the first sequence they give me, the nth term is 3n squared minus 4. So they tell me how to write the nth term. Okay? They tell me how to write the nth term. And again, when n is 1, I'll put a 1 where the n is. When n is 2, I'll put a 2 where the n is, etc. So when n equals 1, I'd have 3 times 1 squared minus 4. 3 times 1 squared is 3. 3 minus 4 is negative 1. When n is 2, I'd have 3 times 2 squared minus 4. 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. When n is 3, I'd have 3 times 3 squared minus 4. 3 squared is 9. 9 times 3 is 27. 27 minus 4 is 23. And when n is 4, okay, I'd have 3 times 4 squared minus 4. 4 squared is 16. 16 times 3, 48. 48 minus 4 is 44. So the first 4 terms would be 1, 8, 23, and 44. That would be the first 4 terms of that sequence. Okay? The second one they give me, they say the nth term, C sub n, is 9 times negative 1/3 to the n. C sub n, 9 times negative 1/3 to the nth power. 9 times negative 1/3 to the nth power. Okay? And they want me to write out the first 4 terms. So again, when n is 1, you get 9 times negative 1/3 to the first. That's 9 times negative 1/3. But 9 times negative 1 is negative 9. Negative 9 divided by 3 is negative 3. When n is 2, you get 9 times negative 1/3 squared. That's 9 times. Negative 1/3 squared gives you 1/9, but 9 times 1/9 is 1. Negative 1/3 squared means negative 1/3 times negative 1/3. That's a positive 1/9, and 9 times 1/9 is 1. When n is 3, you'll have 9 times 1/3, negative 1/3 cubed. Take your calculator, cube negative 1/3, and you'll get negative 1 over 27. Because negative 1 times negative 1 times negative 1 is negative 1. 3 times 3 times 3 is 27. 9 times negative 27 would be negative 9 over 27, which would be negative 1/3. And finally, when n equals 4, you'll have 9 times negative 1/3 to the 4th power. And again, take your calculator. Negative 1 to the 4th power is 1. 3 to the 4th power means 3 times 3 times 3 times 3. That's 81. Then I'll multiply 9 times 1 over 81. You'll get 9 over 81, which is 1/9. So the first 4 terms were negative 3, 1, negative 1/3, and 1/9. Those would be the first 4 terms of the sequence. All right, so these are sequences, and they're just making sure that I know how to write the terms of a sequence if they tell me what the nth term looks like, okay? And again, a sequence will always start with n equals 1, all right? It's a function whose domain is the set of positive integers, okay? Well, when we look at part B, some sequences are positive. All the terms will be positive. That's an example of a positive sequence. This is an example of what we call an alternating sequence, because I alternate from a negative to a positive. First term is negative, second term is positive. Third term is negative, fourth term would be positive. Fifth term would be negative, sixth term would be positive. It's going to keep alternating between negative and positives, okay? So some sequences are what we call alternating series, or sequences rather, okay? And what we want to learn is we're going to write the terms of these sequences recursively. Objective 2 on page 1008. We're going to write the, well, they're going to give us sometimes these sequences, and they're going to give us a definition that's a recursive definition. And we're going to have to look at that definition, and we're going to have to write out the terms of the sequence. What do I mean? Well, example 2 is a good illustration. Example 2. Example 2 says write the first 5 terms of the sequence. Write the first 5 terms of the sequence. Okay? Defined by, they say A1 is 4. So they give me the first term. And they say AN equals 2AN minus 1 plus 1. Okay? And that part definition is only for n greater than 1. This definition is for n greater than 1. Okay? So, when n is 2. So when n is 2, I have to use that recursive definition. So everywhere you have an n, put a 2. So A2 would be 2, A2 minus 1 plus 1. A2 minus 1 is A1. A1 is 4. 2 times 4 is 8 plus 1 is 9. So A2 turns out to be 9. When n is 3, put a 3 everywhere the n was. A3 would be 2A2, because 3 minus 1 would be 2 plus 1. Well, I know what A2 is now. A2 is 9. So that's 2 times 9 plus 1. 18 plus 1 makes 19. When n is 4, use that formula. Everywhere you have an n, put a 4. A sub 4 will be 2A sub 3, right? Because 4 minus 1 makes 3, plus 1. Well, you just found out what A3 is. It's 19 plus 1. That's 38 plus 1, that's 39. okay? So this is what we're talking about, a recursive definition. The next term is always based on what the previous term was, okay? And finally, when n is 5, a sub 5 is 2a sub 4 plus 1. A sub 4 we just found out is 39 plus 1. That's 79. Okay? So the first 4 terms, or first 5 terms, A1 was 4, A2 was 9, A3 was 19, A4 was 39, and A5 was 79. That would be the first 5 terms of that sequence. Okay? All right. They talk about the Fibonacci sequence. You can read that on page 1009. Okay. The next thing we want to talk about, though, is the factorial notation. Factorial notation. Okay. We're on page 1009. Okay. Let n be a positive integer. Let n be a positive integer. Then n factorial, that's an n with an exclamation point. And the way we read this, read n factorial, that's how we'll read it, and how we'll write it. N factorial, okay? So n factorial, they say, is defined, then n factorial is defined as n times n minus 1 times n minus 2 times dot 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 times 2 times 1. Okay? That's how we define it. This is called n factorial. And there's a factorial key on your calculator. You'll see an n with an exclamation point. That's exactly what this key is. Okay? So let's make sure we can calculate factorials. So examples. So 8. 0 factorial is defined to be 1. This one is important. 0 factorial is defined to be 1. You can check it out on your calculator. Enter 0 and then hit that n factorial key, you'll get 1. Okay? 1 factorial, well, that's just 1, 2. C, 2 factorial. Now we're following this thing. 2 factorial, put a 2 in the end one. So 2 times 2 minus 1 is 2. D, 3 factorial. That means 3 times 2 times 1. 3 times 2 times 1 is 6. E, 4 factorial, would mean 4 times 3 times 2 times 1. All it is that integer times each successively smaller integer till you get to 1. So 4 factorial would be 4 times 3 times 2 times 1. 4 times 3 is 12, 12 times 2 is 24. Okay? 5 factorial. That means 5 times 4 times 3 times 2 times 1. And again, do that in your calculator. Do that in your calculator. So that should be 120, I think. So that's how factorials work. Okay? That's how factorials work. It's just that integer multiplied by each successively smaller integer all the way down to 1. You just take the product of all those integers. Or again, just use that key on your calculator. So with that in mind, let's do some of these examples with factorials. Example 3. Okay? And I'm just going to say evaluate. So 8. They give us 8 factorial divided by 3 factorial times 5 factorial. Now again, I didn't write it over here, but remember, 8 factorial will be 8 times 7 times 6 times 5, 4 times 3 times 2 times 1. And since I see a 5 factorial in the bottom, if I wanted to, I could write this as 8 times 7 times 6. All of that, I could say is just 5 factorial. So 8 factorial It's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But again, I can write 5 times 4 times 3 times 2 times 1 is 5 factorial. So when I come over here, I'm not gonna write it all the way down. I'm gonna write 8 times 7 times 6, but then I'm gonna leave it like 5 factorial. Then I've got 3 factorial in the bottom times 5 factorial. These will cancel. That's why I didn't take it all the way down to 1. Those two things cancel. 5 factorial in the top cancels with 5 factorial in the bottom. So now we've got 8 times 7 times 6 over 3 factorial. But we've done 3 factorial. 3 factorial is 3 times 2, or just 6. So 6 in the top will cancel with 6 in the bottom. 3 factorial is 3 times 2, or 6. So 6 in the bottom cancels with 6 in the top. All I got left is 8 times 7, which is 56. So this expression is 56. B. They give us n factorial. Now you could have put all this in your calculator, because your calculator can do factorial arithmetic. This one you cannot put in your calculator. N factorial over n plus 2 factorial. But again, you've got to understand how factorials work. N factorial means n times n times minus 1 times n minus 2, dot, 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 dot. Right? So I know what he looks like. My question though is, what does n plus 2 factorial look like? Well, that'll be n plus 2 times n plus 1. I subtract 1 each time, times n factorial. I'm going to do the same trick. I'm doing the same thing I did here when I had 8 factorial. 8 times 7 times 6 times 5 factorial. Because I know I've got this n factorial in the top. So if I can rewrite this as this, right? Okay? Now I can say these cancel. So I'll have 1 over n plus 2, n plus 1. That'll be my answer. So this is how I'm going to handle these factorial problems. Okay? This is how we're going to handle these factorial problems. Okay. All right. That was example 3. Example 4, they say, given the sequence defined by. Example 4, given the sequence defined by. They say b sub n equals n squared over n plus 1 factorial. B sub n equals n squared n plus 1 factorial. Okay? B sub n equals n squared over n plus 1 factorial. They want me to find b sub 6. Find b sub 6. All that means is everywhere I had an n, I put a 6. So 6 squared, 6 plus 1 factorial. Everywhere I had an n, I put a 6. Okay? Well, now I got to simplify this. 6 squared is 36. Okay? 6 plus 1 factorial means 7 factorial. That's 36 over. 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. That's literally what 7 factorial means. Well, now I can cancel because all of this is multiplication, so I can say 6 goes into 36 6. So I'll have 6 over 7 times 5 times 4 times 3 times 2 times 1. The 6 is gone now because I canceled 6 in the bottom. This 6 canceled with 36. I've got a 6 left in the top, and that 6 is gone, so 7 times 5 times 4 times 3 times 2 times 1. So now I can say 3 goes into 6 twice. But then I can say 2 goes into 2 once. So I'll have 1 over 7 times 5 times 4 times 1 doesn't matter, right? 7 times 5, or 5 times 4 is 20. 20 times 7 is 140. So there's my reduced form. Okay? All right. Hopefully this makes sense. If it doesn't, please reach out to me and let me know. I'll be glad to elaborate further. example 5. Well, example 5 is a little different. Example 5, they give me the terms, and they want me to come up with this definition, okay? So example 5 says, find the nth term an of a sequence. Find the nth term an of a sequence. Okay? Whose first 4 terms are given? Whose first 4 terms are given. Okay? So, A1 is 2/3, 3/4, 4/5, 5/6. Okay? So they give me the first 4 terms. And they want me to write a recursive definition. Okay? So I'm looking for the pattern. So A sub n equals. And look at your numerator. And again, n always starts out with a 1. Okay, n always starts out with a 1. So when n is 1, the numerator is 2. Then the next one is 3, 4, 5. So all I'm looking at now is my numerators. 2, 3, 4, 5. So to go from one term to the next, all I'm doing is adding 1. Okay, all I'm doing is adding 1. But I've got to start out again, when n is 1, I'm going to need a 2 here. So I'm going to say n plus 1 has to be my numerator. Because when n is 1, 1 plus 1 makes 2. When n is 2, 2 plus 1 makes 3. When n is 3, 3 plus 1 makes 4, etc. Now look at your denominator. Well, the same thing happens in the denominator. I'm increasing by 1. 3 to 4 is I add 1. 4 to 5, I add 1. 5 to 6, I add 1. But again, I'm starting out at 3 now. So when n is 1, I need 3. So I better have n plus 2 here. So when n is 1, 1 plus 2 makes 3. When n is 2, 2 plus 2 makes 4. When n is 3, 3 plus 2 makes 5, etc. So there is my definition for my nth term of that sequence. B says, they give me the first 4 terms again. 1/5, negative 4 over 25. Okay? 9 over 125. The 4th term is negative 16 over 625. So there are my first 4 terms. Okay? And again, I want to write a recursive definition for the nth term. So I'm going to call this one Bn. So again, the other thing I see here is this one is an alternating sequence. So positive, then a negative. Positive, then a negative. So whenever you see an alternating sequence, that means negative 1 to some power. Because negative 1 raised to odd powers give you negatives. Negative 1 raised to an even power will give you a positive. So when n is 1, this first term was positive. So when n is 1, the first term is positive. So this negative 1 has to be raised to an even exponent when n is 1. So I'm going to write n plus 1. Because again, check it. When n is 1, negative 1 to the 1 plus 1 means negative 1 squared. That's positive. So the first term will be positive. When n is 2, 2 plus 1 makes 3. Negative 1 to the 3rd power would be a negative quantity. So this will take care of the alternating part. Positive, 2nd term negative, 3rd term positive, 4th term negative, etc. Now look at your numerators. 1, 4, 9, 16. All right? So 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared equals 16. So 1 squared, 2 squared, 3 squared, 4 squared. So when n equals 1, when n equals 2, you square it. When n equals 3, you square it. So really, I'm just going to need n squared. Because again, when n is 1, 1 squared will be a 1. When n is 2, 2 squared will give you a 4. When n is 3, 3 squared will give you a 9. When n is 4, 4 squared will give you 16. So now I've got my numerator taken care of. Now look at your denominator. N is 1, you get 5. N is 2, you get 25. N is 3, you get 125. Well, that just better be 5 to the n. When n is 1, you get a 5 in the bottom. When n is 2, 5 squared is 25. When n is 3, 5 cubed, 125. So there is my nth term. Okay? So you're gonna build that nth term. We saw that we had an alternating sequence, so we knew we needed negative 1 to some power. We wrote that out first, then we looked at the numbers in the numerator, and we saw that it was just n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So that's why I knew I just needed n squared. And I look at all the denominators, and all the denominators are power of 5. So that's how I do that. Okay? The next thing they talk about is summation notation. Summation notation. Okay? And we're on page 1011. Okay? Page 1011. They say given a sequence A1, A2, A dot, 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 the nth partial sum S sub n is an infinite series. Okay? It's a finite series, and it's represented by. So, they say that we're given a sequence. Keeps going forever, right? Then they're defining by what they mean by the nth partial sum, and the way we're going to write it is S sub n. Okay? So we're defining what we mean by the nth partial sum, and it's this. It's going to be A1 plus A2, dot, 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 all the way to n. So all I'm doing is adding up the first n terms of the sequence, okay? And this is a finite series. Okay, this is a finite series. I'm just adding up the first n terms of the series. And when I do that, I can write that. You'll also see them say that Sn equals the sum, I equals 1 to n of ai. This means the same as that. When I is 1, you get A1. And sum means addition. That summation thing means to add. This is called the summation symbol. Looks like a backwards, well, I don't know what that thing is. M flipped over maybe. That is the summation symbol. That just means you're adding these terms. When I is 1, you get him. Plus, when I is 2, you get him. Plus, when I is 3, you get the next one, so on and so forth. So this is the same as that. So I can write this. Okay? They are the same thing. They mean the exact same thing. Okay? All right, and that little I, that index I, that does not mean I equals the square root of negative 1. That is not complex number notation. That's just my index for my series. Okay? All right, now this is a finite series now, because I'm adding them up. It was a sequence when I was just listing them out. There's a difference. This is a sequence. This is a series. Okay? All right, let's see if we can understand this series notation. So we're at example 6. Let's make sure we understand the series notation. So example 6, this says, write the terms for each series, right? Terms for each series. We're talking about series now instead of sequences. And evaluate the sum. And evaluate the sum. So, A, they give us the sum. I equals 1 to 5. And they say 2i plus 3. Sum I equals 1 to 5, 2i plus 3. Okay? All right, well, when I equals 1, and they said the first, so 5. So I equals 1 to 5. So when I equals 1, put a 1 where the I is. So that's 2 times 1 plus 3. Okay? Plus, when I is 2, you'd have 2 times 2 plus 3. When I is 3, you'd have 2 times 3 plus 3. When I is 4, you'd have 2 times 4 plus 3. And finally, when I is 5, you'll have 2 times 5 plus 3. 2 plus 3 makes 5 plus. And again, this was when I was 1. This one right here was I equals 2. this one right here was I equals 3. This one right here, I equals 4. I equals 5. I want to make sure it's clear how we're getting these numbers. We're going to sum from 1 to 5, 2i plus 3. So this first one, I is 1, I get 5. 2 times 2 is 4, 4 plus 3 makes us 7. That's what the I equals 2 term is. 2 times 3 is 6, 6 plus 3 is 9. 2 times 4 is 8, 8 plus 3 is 11. 2 times 5 is 10, 10 plus 3 is 13. And they want me to find the sum. So I've written the terms. Now I want to find the sum. Just take your calculator and add these 5 numbers up, and you'll get 45. Okay? B, the sum, K equals 3 to 6. And they say negative 1 to the K, okay, 1 over K. Now we notice that the index this time starts at 3. An index can start at anywhere. It can start at 0, well, not anywhere. 0 or anything positive is where your index will usually start from. 0 or anything positive, okay? So the index does not have to start at 1. This index starts at 3. So when K equals 3, I'm going from 3 to 6, right? From 3 to 6. So when K equals 3, just write it out. You'll have negative 1 cubed 1/3 plus, because again, summation means plus. You're adding all the terms together. That's what the summation symbol means. You're going to sum the terms. So when K equals 4, negative 1 to the 4, 1/4. When K equals 5, negative 1 to the 5, 1/5. And finally, when K equals 6, that would be those first terms from K equals 3 to 6. Now all I got to do is evaluate. Negative 1 cubed is a negative, so this is negative 1/3. Negative 1 to a even exponent, negative 1 to the 4th, take your calculator, is a positive 1, so plus 1/4. Negative 1 to the 5 is a negative, so minus 1/5. And then negative 1 to the 6 is a positive 1/6. So you're going to have negative 1/3 plus 1/4 minus 1/5 plus 1/6. Take your calculator and add all those things together. You'll get negative 7/60. So the sum of that series would be negative 7/60. Finally, C, the sum n equals 1 to 6 is 3. The sum n equals 1 to 6 is 3. Well, that's the easiest one of all. When n is 1, 3. When n is 2, 3. When n is 3, 3. When n is 4, 3. When n is 5, 3. When n is 6, 3. It's just 3. You're adding 3 up 6 times. Well, 6 times 3 is 18. Or 3 plus 3 plus 3 plus 3 plus 3 plus 3 is 18. All right. All right. Finally, example 7. Example 7 on the next page says write each sum using summation notation. Write each sum using summation notation. Okay? So A, square root of 3 over 1 factorial plus square root of 4 over 2 factorial plus square root of 5 over 3 factorial, dot, 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 okay, plus square root of n plus 2 over n factorial, okay? All right. So I want to write this with summation notation. So here they gave me the summation notation, right? That's what I want to do. I want to write this with that sum notation. Sum I equals 1 to 5 and 2I plus 3, that kind of thing. Well, this one is pretty easy because this last term pretty much tells me what I gotta have. Okay? And again, I started out with n being 1. Right? N equals 1, 2, 1, 2, 3, all the way up to n. And let's say I. Okay? So there it is. Easy stuff. B, 2 over 1 minus 3 over 4. Plus, they say 4/9 minus 5/16. Plus 6 over 25. Okay, equals. So again, I want to write this with summation notation. Well, again, 2, 3, and I got a negative, positive, negative, positive, negative. So I know I got to have that -1 to some power. And again, when n is 1, it's positive, so I can say n plus 1. Okay? So when n is 1, -1 to the second power would be positive. When n is 2, all right? N is 2, 2 plus 1 is 3, -1 to the third power would be negative. When n is 3, -1 to the 3 plus 1 fourth power would be positive, etc. So that takes care of the signs. Well now, 2, 3, 4, okay? And again, I'm going to use j. J equals 1. So if I say j equals 1, then again, this would be j plus 2. Okay? Or j plus 1, I'm sorry. J plus 1. Because when j is 1, 1 plus 1 will make a 2. When j is 2, 2 plus 1 will make a 3. When j is 3, 3 plus 1 will make a 4. So that takes care of that number in the bottom, in the top. Now, 1, 4, 9, 16. 1 squared gives you 1. 2 squared gives you a 4. 3 squared, so this will just be j. This will just be j squared. Sorry, that's just j squared. Okay. So there's our, and again, I need to go 1, 2, 3, 4, 5. So this goes to 5, sorry. So there's our last example. On page 1013, they give us some nice properties of summation. On 1013, they give us some nice properties of summation. Okay. So look at the properties of summation. Those are going to be important, so make sure you look at those. They don't do any examples with them, but we'll do some before it's all over. This concludes section 11.1.